Hello everyone and welcome to a new video. In this video we will discuss metals and many-body interactions. Today's topic is metals and in particular the fact that they exhibit many-body effects. So far we covered materials that can be well described by two-body potentials. For example, ionic materials, any van der Waals interaction. Once we go to covalent materials, then three-body interactions become also important. But for metals, many-body effects are very important. So in metals, early attempts to describe them were using pair potentials, uh, just like Lennard-Jones. So for example, Lennard-Jones potential. And in fact, I would say this is not only early attempts, there are even relatively, I wouldn't say recent, but relatively recent attempts, for example, in 2008, to develop new sets of Lennard-Jones potential for FCC metals. And I think this paper here in 2008 was subsequently followed by other attempts. And this is quite useful. Let's not dismiss the importance of this. The beautiful thing about having Lennard-Jones potentials to describe metals is now we can, in a consistent way, in a physically consistent way, discuss other materials interaction, for example, proteins, covalent materials, any other material, because there is an easy way to discuss or to describe the cross-linkage or the cross-interaction terms between two materials described by Lennard-Jones potentials. We didn't discuss this in our videos, but this is easy to find in literature, the so-called mixing rules. If you have two materials described by Lennard-Jones potential, and you want to have a cross term, for example, let's say you have iron and some carbon in a protein, and you have Lennard-Jones for iron, you have Lennard-Jones for the carbon, then there is a mixing rule that allows you to calculate the cross interaction. So that's quite useful. But in fact, because metals exhibit what is known as many-body effects, uh, bare potentials fail in describing some characteristics of metals. Again, we are not dismissing these attempts, but let's clarify the origin of this. So if we open a new page here and discuss many body effects, let's start with a very simple picture. Suppose I have some central atom in a metal, consider certain metal, and then you have neighbors for that atom. For example, in FCC materials, you typically have 12 neighbors. So you have like 4 in this plane, and I'll try to describe it as much as we can here. There are also 4 in other directions. I think this is not a good drawing here. So as much as we can. So let's say 6 and another maybe 8 here. This is really not drawn well in 3 dimensions, but just to illustrate the idea. Suppose you have a central metal atom and it is connected with 12 neighbors, as for example in FCC materials. Then you would say, look, it's an easy counting here. So I have one atom, a central atom, and it's connected with 12 bonds. So I have created 12 bonds. Then sort of the gain in energy or the cohesive energy per atom here is so the gain per atom, the red atom, is 12 divided by 2, which is 6 bond energy. The reason why I divide by 2, because each one of these bonds, for example, this bond here, is shared between 2 atoms, between this green atom and the central red atom here. So that's why if I want to calculate the gain per atom, this bond is shared between 2, so each one takes half a bond, right? And now the central atom created 12 bonds, so it managed to have or gain or to form 6 bonds in the material, and the cohesion per that atom is the energy of 6 bonds, roughly. Now that means that if you think about it, the cohesive energy, if it was a simple counting like this, then it should be proportional to the number of nearest neighbors, which, if you allow me to denote it with the letter Z, for example, as was used in the early literature, then I would say that the cohesive energy, which if you also allow me to represent it with E sub C, is proportional to the number of nearest neighbors. Of course, if the number of nearest neighbor is less, let's say eight nearest neighbor, as for example in BCC metals, body-centered cubic metals, then the cohesive should be less. This is exactly the picture where you have the proportionality with the nearest number of atoms. This is exactly the picture for pair potentials. So pair potentials, because in pair potentials, the red atom here, the central red atom, when it interacts with, let's say, this white atom here, it doesn't care about the other 11. It doesn't care whether the other 11 are there or not, because it's a pair potential. All what matters, the distance between these two atoms, regardless of the surrounding atoms. Now, this is the picture if you discuss it using pair potentials. However, in real metals, because of many body effects, the cohesive energy is not proportional to the number of nearest neighbors. In fact, there is some experimental evidence and also quantum mechanical calculations that shows that roughly this proportionality should go as the square root of the number of neighbors. Which means if you want if you remember, if you want to, for example, plot EC versus Z, if it was a strict proportionality, it should be a straight line, while if it's a square root function, it should go like this, which means that as the number of neighbors increases, the cohesive energy does not increase in a linear fashion, but in a sublinear fashion, in a square root fashion, which means that when you consider the interaction, again, let's go to this picture here between the central red atom and let's say this blue atom here, you cannot calculate this interaction in isolation from the other 11, because this bond feels the presence of the other 11 atoms. And that's the many body effect. That what you see here is the many body effect in metals. So in metals, you cannot describe it with a simple Lennard-Jones potential or any pair potential simply because of this. Each bond is not individual. Instead, it feels the neighboring environment. Now, in this video and in an upcoming one, we will discuss the manifestation or the result of describing, or the failures in describing metals with pair potential. And let's start with the first one today. So in this video, so failure of pair potentials in describing metals. And in fact, I will discuss two aspects, the so-called vacancy formation energy. It's a very important quantity, and that we will discuss in this video. And in a subsequent video, we'll discuss the so-called surface relaxation in metal. So let's start with the vacancy formation energy. So vacancy formation energy, which is typically we denote it by E formation V, something along these lines, depending on the kind of lead. Or sometimes actually we flip, maybe allow me to do this in this page. Sometimes we actually flip the notation here. Well, both of them are fine. It's just a notation. So maybe form vacancy, there is a V here and F here. So the formation energy of the vacancy. So let's see. The formation energy of the vacancy can be understood in a simple balance, simple thermodynamic balance. So I have a crystal with perfect. So that was really the initial state. So this is state number one. This is a perfect crystal. It has n atoms, and then it undergoes some reaction and it goes to state number two, where now it's not a perfect crystal, it's a defective crystal, and it has n minus one atoms. Now, where did uh, how this happened? What happened is you have a defective, you created a vacant site here, and then you still have, of course, to maintain the balance, you have n atoms here, so plus one atom, because initially you had n atoms and you ended up with n minus one and one. So now let's write the balance here. The vacancy formation energy is um, the energy. Usually in physics, you calculate change. So state number two minus state number one. So state number two, it is the energy of n minus one atoms plus the energy of the single atom. And allow me for a second to call it the cohesive energy. And I will explain why this is the case. The cohesive energy per atom minus the energy of n atoms. So it's a simple balance. You have two states. Each one of them has n atoms. State number two, you have a crystal with n minus one atoms plus one separate atom. And that's why you have a vacancy here. You created a vacancy. And then state one is where you have a perfect crystal. And by the way, vacancies naturally exist in materials as long as you are at a finite temperature, at a non-zero Kelvin temperature. There will always be vacancies. Materials only differ by how much vacancies you have, and typically as you increase the temperature, these vacancies increase. So this is an expression for the vacancy formation energy. But there is something a little bit strange here, which is the cohesive energy. And this is really special for metals, I would say, or for solid state. Why? Because the understanding is that when one atom leaves its place in the crystal to create the vacancy, right? This atom does not go to gas phase. That doesn't go to the surrounding atmosphere that surrounds the crystal. Instead, it actually goes somewhere else in the crystal, build the crystal. In fact, the crystal surface increases up a little bit. So you start building one unit above. This is not a vacancy, because the atom that was here, not necessarily the very same atom has gone to the surface, but it might have gone to somewhere else in the crystal and some other atom went to the surface. And the net effect is that you manage to increase the size of the crystal, right, by building an extra layer. Uh, this is not always the case in all materials. It's all solid state materials. Sometimes the atom that created the vacancy simply goes to vacuum, to the surrounding atmosphere. And this is usually the case in metal oxides and ionic materials, for example. But for metals, the understanding is no, let's say this is nickel, for example, this is nickel metal. When you create the vacancy, you don't get a vapor of nickel around the metal. Instead, this nickel atom just builds the crystal further. That's why we are not really putting here the energy of a single atom alone in vacuum. Instead, we put it when this atom in the crystal, right? And that's why it's called the cohesive energy. If you want to define the cohesive energy more formally, let's go to another slide. So the cohesive energy, again, which I will denote by EC, with a simple balance, a simple thermodynamic balance. Again, state number one, it's like always as in thermodynamics, I have a state number one and state number two. So in state one, I have n separate atoms. So n atoms separated from each other. In a sense, you can consider them as gas atoms. And then in state number two, I still have the same n atoms, but now they are in a crystal. So again, still n atoms, but they are in a crystal. Now, if I want to calculate the cohesive energy per atom, so it's the energy of the state number 2, which is E of N, that's really a crystal energy, minus state number 1, N atoms times the energy of each atom alone uh, in gas phase, for example, divided by the whole thing is divided by N because you want it to be a normalized quantity or a quantity per atom. So this is the cohesive energy per atom, per atom. So that's why I divided by N. It is like the energy of the atom of the crystal or the share of each atom of the crystal, right? Of the cohesion of the crystal. So if you go back to the vacancy formation energy, it is this thermodynamic balance between state 2 and state 1. But instead of putting the energy per atom as an energy of an atom in a gas phase, instead you put it as an atom inside a crystal, right? Because in metals, it really doesn't go to gas phase. Now, how is this related to our topic? The relation is as follows, and we will explain it in a second. If we go to this slide and explain the failure issue here, if you take the vacancy formation energy and divide it by the cohesive energy and take the absolute value, because they usually differ in sign. Typically, the sign convention is that this is negative, right? That means actually that the energy of the crystal is less than the energy of the separated atom, which makes sense. That's actually the driving force for the crystals to form. And the opposite of this is that the vacancy formation energy is positive. And actually, this also makes sense. It's an endothermic reaction. Otherwise, I mean, endothermic if you consider energies alone. We don't want to go into details in this point, but if you only consider energetics, the vacancy formation energy is always positive. It only becomes negative when you consider the overall free energy of the crystal, but that's for another topic. For us here, it's actually positive, the vacancy formation energy. Now, if you take the absolute value of this ratio, it really equals sharp 1 for pair potentials, like Lennard-Jones. Something like Lennard-Jones gives you 1, maybe 0.9999 because of some relaxations effect, which we will discuss now, but it is really 1. This one is fine if you describe a crystal of argon, for example, which is a rare gas. Rare argon, when it crystallizes, actually crystallizes in the FCC crystal structure, and you really get like 0.95, which means that pair potentials like Lennard-Jones are well describing crystals of perfect gases or ideal gases like argon, because really they interact with van der Waals only. So they are really good description for argon. But if you take actual metals, and this was shown in literature, if you take nickel, for example, nickel metal, then look at this ratio. This ratio goes down to about 0.3. If you take another metal like gold, this actually ratio goes way, way down to like 0.23 or even less, depending on how you do the calculation. The moral of the story is that pair potentials predict sharp 1 for this ratio. The vacancy formation energy divided by the cohesive energy, absolute sense, should be 1. And that's fine for ideal gases, but it's not fine for metals. Why this is the case? It is really due to the many body effect that we explained earlier. That's to say, many body effect, which we described here, is that each bond in a metal is sensing the other bonds, right? So that's really the reason why in metals, the overall vacancy formation energy, when you take the ratio, the pair with the cohesive energy, it is less than 1. To dig deeper into this, we can actually have a closer look at pair potentials and how do we get the value of 1. This is easy to calculate with the pen and paper. In fact, in the exercises, we will show how this also ratio by a software package, how it's actually calculated to be 1 also. But then if you include many body effects for metals, this actually goes down to zero point 0.3 or zero point 0.2 depending on the type of the metal. So let's see computing E formation for the vacancy using pair potential. And let's consider for this case FCC metal. In the theory of FCC metals, face-centered cubic metals, the number of nearest neighbors is 12. So there are the number of nearest neighboring atoms in FCC crystals is 12. And that means if you try to calculate this, um, you create a vacancy. So remember in the state number 2, so there is a state 2 and there is a state 1. Or one way or another way, that's the previous calculation that we did with the equation, which we will actually use in the exercises. But here, since it's an easy pen and paper calculation, we can think of it in a different way. What did we lose and what did we gain? We lost, when we created the vacancy, we broke 12 bonds. So we lost 12 bond energies. So I lost here minus 12 bond energy. Let me call it EB, right? So I lost 12 bonds. But what did I gain? Per atom, again, per atom, I gained the following. Remember, if we go back to the picture here, what happened is that this atom managed to go somewhere in the crystal and you gain the cohesive energy. And how much is the cohesive energy per atom is 6 bonds. Why 6? Again, let's go one step further, because in FCC metals, when an atom forms 12 bonds, its share is 6, right? Because each bond is shared among 2 atoms. Let's go back to this pen and paper calculation. So I gained 6 bond energies. So let's do the subtraction, the algebra here. So you get minus 6E bond. But wait a second, the cohesive energy is plus 6EB. And the formation energy of the vacancy is minus 6EB. That means that E formation vacancy divided by E cohesive absolute is actually 1. So for pair potentials, and in fact, what you get with a software package will be like 0.9995 or something like this. The reason is when you remove the atom and generate the vacancy, you actually have some relaxation around it. In other words, the 12 neighbors, they don't stay in their static places. Instead, they might relax inwardly or outwardly, depending on the material and the type of the interaction, getting closer or further away from the vacancy, right? So yes, so let's summarize what we have discussed so far in this video. We said early attempts and even recent ones to describe metals, they were using pair potentials, Lennard-Jones in particular. And this is quite nice, especially if you want to study, let's say, metal protein interaction or metal ionic material interaction in a simplified way, of course. Now, the problem is pair potentials are not good description for metals. The reason is the many body effects. Pair potentials dictates proportionality between the number of bonds and the cohesion or the cohesive energy per atom. Meanwhile, quantum mechanics and experiments show that the relationship between the cohesion and the number of neighbors is not linear. Actually, it's sublinear. This has implications. When you use pair potentials to describe metals, you fail in describing vacancy formation energy and surface relaxation. In this video, we discussed how this failure of vacancy formation energy is happening. So what's happening is that for pair potentials, the formation energy, the vacancy to cohesive energy gives you sharp 1. But in actual metals, it's like 0.3 or less, or a little bit more, of course, depending on the metal. In a subsequent video, we'll go back and discuss the surface relaxation issue. And finally, we will discuss how to include many body effects for metals to rectify these two failures. And in fact, there are other failures as well. For example, in describing the mechanical properties and the elastic constants for methods. Thank you so much and see you in another video.